Okay. So the question was, why do we have inferential statistics? What's the reason? I mean, why are you sitting here learning how to do this stuff? And the reason is prediction, um, but it goes beyond that, right? It helps us understand why things aren't the way that we would expect them to be. So, for example, if everyone was exactly 6 feet tall, we would never need to predict height, right? We would know there's no guesswork about it. But that's not necessarily the case. Now, if every man was 6 feet tall and every woman was 5 feet tall, then we would know that the average height is what? Yeah, 5.5, right? Assuming the 50-50 distribution, right? 5 feet, 6 inches would be the average height. And we could get a more refined value of someone's height if we knew what their gender was or biosex was, right? And so if we knew that a person's biosex was male, then we would take the average height and we would add 6 inches, right? If we knew that they were female, we would take the average height and we would subtract 6 inches. And we all learned how to do this in grade school using a mathematical equation. And what was that equation? Yes, y equals mx plus b. Who learned it as m and who learned it as a? Okay, slope is m, right? We learned slope as m. Every once in a while, somebody will say that they learned slope as a. And now we're going to confuse everything because in statistics, we use y equals mx plus b plus e, right? And we no longer call the slope m, we call it b, but unfortunately we had a name for b already, and b was what before? The intercept, and now the intercept is going to become a or I, right? So y equals bx plus I plus e. What's e? Error, right? Because we always have error. And so technically, when we're doing this, we don't say y equals, um, yeah, I mean, when we delete the e, when we remove the e, then we say something a little bit different, right? And what is the little bit different thing? We're no longer predicting y, we're predicting what? Y hat, right? Our expected value of y, yeah. So when I've taught this class in the past, I've spent a lot of time talking about correlations and what correlation is and how you get to a correlation. So let's talk just a little bit because in the end, correlation and a correlation coefficient and a regression coefficient are the exact same thing, right? At least in the bivariate model. And all we're going to be talking about today is the bivariate model. But what is the correlation between, or I mean, what is the relationship between a correlation coefficient and a slope coefficient? In what differentiates those two? Anybody know? So it's just standardization, right? One of those is standardized and one of those is not standardized. And when you standardize something, we do what? If we standardize a variable, what does that mean that we do to that variable? We mean center it and we do something else. So standardizing, mean centering is just setting the mean to be 0, right? Well, we do something else when we standardize a variable. Yeah, we do what with the standard deviation? You do make it 1, and how do we get that to be 1 then? How do we make a variable so that the standard deviation is now 1? You make it a z-score. How do we make a variable into a z-score? And how do we do that? You're right. You guys are all right. I'm just saying, like, how do you do it? It's like saying, like, I'm saying, you guys are saying, like, make a pie, and I'm saying, yeah. How do we make a pie? What are the ingredients? How do we make something into a z-score? What is a z-score? Let's start with that. There's two things that define a z-score. What are they? Has a mean of 0 and a standard deviation of 1. So if we have a variable, a non-standardized variable, how do we make that variable z?
Plug it.
Yeah, plug it into the formula. All right, everybody open up Excel. Let's do something here. Okay, so let's just call this V1.
Difference over dispersion.
Oh, that brought it back.
Actually, you know what? Let's do this. I'm just going to copy this stuff here. So open up Excel and let's plug these numbers into Excel. This is actually the data from this chapter. Who read chapter 2, by the way? Everybody watched the video. Who read chapter 2? It reads like, to take a quote from a great movie, I'll be honest. Reads like stereo instructions. Who knows what movie that's from?
Reads like.
Stereo instructions.
That sounds like an 80s thing.
It is an 80s thing,
Right,
and they say it over and over throughout this movie. Nobody knows? It's Beetlejuice. It comes from Beetlejuice. I will throw out all kinds of 80s movie references. I'd love to do that. Just out of curiosity, who has seen the movie? Who has not seen the movie Groundhog Day? Oh, you guys are missing out. That is such a good movie. I think that I don't know. There are few movies better than Groundhog Day. It's not even my favorite movie or even in my top 10, but it's a great movie. I love it. Okay, so do we have all of these numbers plugged in?
Yeah, 48.
I just got contacts, so I'm very visually
Oh,
see all of the things more finally.
wait, Matt, you need to get We're just let's get Matt contacts for his birthday.
Okay, and once you have those plugged in, actually let's right here, let's write mean SD. Who here is great with Excel, knows all of the Excel formulas and codes to plug in? Nobody? Awesome. That's what I was hoping you would say. We have 15 different observations here, right? And we have variable 1 and we have variable 2. Let's start. In order to calculate a z-score, we're going to need to know the mean. Why do we need to know the mean?
Like x minus the mean divided by standard deviation.
Oh, so that is how we calculate a z-score. Just FYI. There is the ingredients for the pie that I was looking for. It is x, x minus the mean divided by the standard deviation. So we need to find the mean and the standard deviation for each of these variables. Let's find the mean first. Let's go equals sum all of these divided by 15. That is our mean for that. Let's go equals sum all of these divided by 15, and that is our mean for variable 2. What is our formula for standard deviation?
That's the formula. Square root of variance.
Okay, the square root of variance. Very good. So in order to find the standard deviation, we have to do a couple of things first, right? What do we have to do?
You have to find the difference between the score and mean, and then do something else with it.
Okay, so let's start by finding the difference between the score and the mean. That is called what?
Some squares.
Not yet.
Square.
It's just called our deviation, right? Like, so we have V1D is equal to this value minus this value. And for my Excel wizards, we need to do something else to make this work. What do we have to do? If we're going to grab that and then drag it down to make it apply to everything, what do we do? Well, you do have to take the corner. It's not an exclamation, though. It's actually, it's a money sign. Yep, dollar sign.
And it basically just
So it will lock that value, and then if you drag this down, right now it's at B2. If I move this down, it will be at B3, right? Move it down one more, B4, and we can drag it all the way down to the bottom. And there is our,
so it's like row and column. Each dollar sign.
Can you double click on the first one again, please? To show us the.
So dollar sign blocks the value that the dollar sign store out.
Well, if you put it in front of the row and then put it in front of the column, so whichever one you want.
is that better?
Oh, so it was like dollar sign B, dollar sign 17. So it like finds the.
Oh, I can make that bigger, and it doesn't actually change this, unfortunately.
Oh, that's so.
I can see.
You can drag it. Cursor and that's when you- that's when you-
Is that just some? Is that just some? Oh, so okay, some.
Yeah.
Is it more insert?
So this is so much squares.
Okay, now we need to get our squared deviations, right? And so to get our squared deviations, we just put equals this time, or I mean, whoops, right? Caret, I'm sorry, I said times, but it's caret, so that's squared, right? And then drag that down.
May I have your attention, please? The fire alarm system is under test. Please disregard all emergency evacuation signals. I repeat, the fire alarm system
Fun.
is under test. Please disregard all emergency evacuation signals.
Everybody up to this point right now, we have all of our squared deviations, right? There you go. Equals, oops, should be the sum of these.
What is the meaning?
What's that?
Oh, we just went ahead when I got confused.
Oh, gotcha.
I'm caught up. It's not like it's,
Find it.
it's, formula sheet.
I'm looking.
Remember the one you used for the exam?
Oh, okay, me either, but.
You get a really Yeah, so we've done this. Okay, and minus one.
Yeah, that's the weird way.
That was what you guys.
Is there another way?
You guys doing something else?
No, I'm trying to find the. Is there a computational version of the standardization formula?
Is there a what?
Computational version of the
Yeah.
formula? I mean, it looks different. The format is a little different.
Hold on. Should we Google this quick? Standard deviation formula. Math is fun.
Math is fun. Yay.
So that's this.
Okay,
This
yeah.
is the formula. It doesn't look great, right?
See, I'm thinking of this one. That one. It's good. Well, I mean, you would square root it.
Sure. Yeah. Okay.
We call that one the computational. No, I just like this one.
Oh, that's different than what's on my list too.
Yeah.
We're gonna show them.
Well, you square root. It's because I don't know math.
No, but Saba has it not like where you divide the squared x over x. Saba's doing that then.
Huh?
Yeah. Yours is x minus x squared, or x bar minus x squared.
Relax.
Wait, yours doesn't ever have the mean.
What? What do you mean? I don't need it.
This is.
Okay. So we have now our sum of squared deviations, right? And now we need to do. We can come over here and go equals square root this divided by what? N minus 1, which is 14 in this case, right? That number doesn't quite look right.
Yeah, I got 1.2. Wait.
You got 1.2?
Square root. Oh, what? Is it square root? Is it square root of the entire thing, or square root of just the sum squares? Or
Oh, you know what? Actually, I think you are right. So if we go equals square root this.
should not be that.
No, that's not right. I'm sorry.
Wait, is my value right?
Okay. What did I have before? Equals square root of this divided by 14. I think that's right. Here's how we can check though. This is the formula that you can plug in this formula. Oh, why did I go through all of that work, right? Yeah, that's right. So we
I love it when we go into that way. They're like, we usually actually do it. Like, oh.
So we've calculated the mean and the standard deviation, right? Now let's calculate z of variable 1. So what was our formula to calculate z again?
Like x minus x bar over standard deviation.
X minus x bar, the sum of x minus, well, yeah, I'm sorry, for each individual observation, it's x minus x bar divided by standard deviation. Exactly. So let's go equals this. We should probably use parentheses. This minus this. We're going to need to put dollar signs in there, right? Divided by this. We will also need our dollar signs in there. And so that is our z-score. And actually, we can kind of look at this and we can say like, okay, so the mean is 7.6666 on forever. Do we have a value here close to the mean? We've got a 7. We've got an 8, which means that when we calculate these z-scores out, this should be very close to 0, but just a little bit on the positive side, right? This should be very close to 0, but just a little bit on the negative side. So let's grab this. Let's pull it down. There's our z-scores. Yep, very close to 0, a little bit on the positive side. Very close to 0, a little bit on the negative side. And if we go like this, I think this works. Oh, no, is it average? I think you have to do average. What should our average be here? Oh, yes. What should our average be when we do this? It should be 0, right? And now if we want to calculate our standard deviation of this value, what do?
Sorry.
How do we calculate the standard deviation of this value?
Of that distribution.
Yeah.
Do it again. Do the standard deviation formula. Or
You're right. Yep.
yeah, we're gonna do it.
So we don't actually need to do this, right? It's already centered. Like that's done. So all we really have to do is square this, right? And then divide by what? And then divide by n minus 1 and take the square root of that, right? Okay, so we're not going to worry about that right now. But let's go back and let's do everything that we just did for variable 1, except for now for variable 2. So if we go v2d, what was v1d again?
Sorry. I just keep looking up and down. I just get lost.
What was v1d? Okay, so we are going to go x minus mean, right? Now we have our new different scores. And if we want v2 squared difference, we're going to go this times, or I mean squared. Why do we square this, by the way? Why do we have to square these ones?
Because otherwise your numerator would be 0.
Yeah, we're trying to get to a sum, right? And what is the sum of these differences?
0.
It's 0, right? Sum of these differences is going to be 0. So we square them, make everything positive, so that when we want to get our sum of differences, they're all on the positive side. So
Very
yeah,
random question.
Shoot.
Is there a lot of work in the space of not squaring it and doing something different, like adding a constant or something else? There's like a whole area of stats that doesn't do the whole squaring of the difference.
gosh, I don't even know.
Okay, just curious.
Yeah.
Because obviously it creates problems with like those, like like the extreme values are like bigger because they're squared than the ones closer to them.
Oh yeah, but we do eventually then take the square root, right? So that pulls those values right back down to where they are, or where they should be,
That is the difference in values.
which were squared.
Mm-hmm.
So yeah, I mean, I don't know if this is true. I want to say that. I'm not going to say it. No. Okay. All right. So we have this value here, and now we can use this value to calculate our standard deviation. So it is this.
Divided by.
Oops. I'm sorry. The square root of this divided by 14, right? And our standard deviation should be 13. We can check that. Equals STDEV. Yeah, so we're right on. Everybody up to speed right now? We all in the same spot? Cool. So all we've done right now is calculated the z-score for each thing, right? in bivariate regression, a bivariate regression coefficient, I said, is the exact same thing as a correlation, with the exception that the bivariate correlation coefficient is not standardized. I mean, the correlation coefficient is standardized, but the bivariate slope is unstandardized, right? So if you, there is a couple of formulas, but if you turn to page 29 in your book, you're going to see the formula for calculating a correlation coefficient. It's 2.3.2.
Do you want us to be bringing our books, by the way?
Oh, did nobody bring their books? Oh, okay. It is a ridiculously long formula. That's the only point that I wanted to make here.
Should we bring our books?
It wouldn't hurt. So this is the formula, right? It is crazy long. I'm going to show you a much faster way to calculate the bivariate correlation. But that formula is taking into account the fact that there is that these associations are not standardized, right? And so it's trying to zero in on the association accounting for whatever the mean is in one of those variables, and y in this case, right? In order to find the bivariate correlation, it's actually super easy. We've already calculated our two z-scores, right? The bivariate correlation is really just the relationship between z-scores. That makes it automatically standardized, right? So if we do, let me see here. It's the easiest way to do this. Yeah. Okay, so let's make let's make a multiplicative factor. Let me see if I already have the. All right. So let's start by doing z1 minus z2. This is going to give us what is this going to do? It's essentially, when we think of a correlation, we have a coefficient, right, of some amount, and we often like to think of that coefficient being representative of a line through our data, right? And that the strength of that coefficient is a function of that line. And that is true when it's unstandardized. But when it is standardized, it's a little bit different, because the strength of the association is no longer the shape of the line, or the degree to which the line is pushed up or pushed down, but it's the degree to which data points are clustered around that line, right? That's what is the measure of a strong correlation. So what we want to do first is figure out what the difference is between each of these z-scores at each time point, right? So we're going to start by subtracting z1. Oh shoot, we did not make z2 yet. Or v2 zv2 equals this. Why did that not work? Oh, it did. It's just putting it up here. All right, equals this. What? What do we do next? How do we make a z-score?
You subtract the mean.
Minus this.
Yep.
With dollar signs.
I love that trick.
Oh,
I feel like I've always retested every time. So this is just.
it gets better. So divided by standard deviation, thank you. Okay, and we need to put the dollar signs in here too. Now you can actually this is a complete aside, which I tend to do. FYI. Whoops, did I miss that? Let's see. You could, if you wanted, So sometimes you want to like drag a formula across, and you want like one piece of that to stay consistent and one not. When we get into graphing interactions, we're going to be doing this a lot, and so you'll put the dollar sign just in front of the letter or just in front of the number, and it will hold things constant in a row versus a column, right? So it's actually it's super helpful. Okay, so that is our formula for. Why did they do that? Why is it doing this? Stupid Excel, you gotta be kidding me. Okay, let's try this again. Look at, they're still there. Okay. I'm gonna pretend like that thing doesn't really exist. I'm gonna go like this. Delete. Ah! That didn't work. Can I do that? Where's the...
Yeah, if you like right click on the column, yeah, here.
No. Any other suggestions?
What's the problem? Should I do that?
This thing, like my Excel is like stuck for some reason.
Oh, it like glitch.
Maybe under home up top. That's where you have all your buttons, right on the left. Yep. And then you can select cell I2, and then do the.
Just drag it over. You think that'll do something?
format.
Shit, that didn't work
Oh,
either.
he's broken. You need it.
I wrote the region. I just couldn't.
What?
Oh, you did something.
Yeah, I just did that, and it doesn't move.
Oh, you could just minimize the program and then like restore it.
You think that'll work?
Yeah, sometimes that works with like display issues.
Yeah.
No,
Ugh.
you're broken. Restart.
This is driving me crazy.
I think you need to save and close.
All right, let's try that. File, save as, desktop, CTO.
Also, I'm only pushing screen for like organizing like my study guides and stuff.
What's wrong?
Ah, that worked. I mean, it got rid of it. Okay, so let's go v1 equals,
You mean V2, right?
oops. Yes, v2. ZV2 equals, it just did it again, didn't it? Okay, it didn't quite do it. Okay, equals this minus this divided by this, and then I'll just come up here and fix these. I don't think I've ever had that happen before. Oops. There we go, that worked. All right, so here are our z-scores for this.
Now you're gonna subtract.
Yes, so now we need to go z1 minus z2. So that will be equals this minus this. We're going to have the same issue that we had before, right? If we add these up, they're going to be 0. So now we need to get z1, z2 squared deviations, which is just this squared. Pull that down, equals sum of our squared deviations our squared standardized deviations, right? So now we have 9.61367139. This is the total of our squared deviations. And a correlation is really just the average of our squared deviations. So, how do we get the average of our squared deviations?
You're going to divide by n minus 1.
We are going to divide by n, but it's actually, we're talking about two different variables at this point, right? We're talking about the overlap of two different variables. So it's not n minus 2, it is xn minus 1 plus yn minus 1, which is 28. So if we go equals this divided by 28, does that look like a correlation?
Has the appearance of one.
It has the appearance of a correlation. It ranges between minus 1 and plus 1, right? But it's not the actual correlation. And in fact, we can find out what the correlation is by doing something very simple. We highlight these two variables, and we say equals, I think it's core, right? Coral. C-O, oops.
It's the sum of
You know, coral, like that. And then do we put this? Oh, shoot, I messed that up.
say 15 plus minus 1 plus 15. Yeah.
Is that how we do it? Will that work? Or do we have to have like,
I didn't do it like that.
you have to have one row and then a comma and then another row, right?
Yeah. But in the same parentheses.
That's what I was thinking. Whoops. Okay. Comma. There, that should work. Our correlations don't match. What is going on there? Hey, where'd my other correlation go also? Oh, is it just over further? I'm just going to go equals this. So we can put them side by side. Our correlations don't match. Anybody know what is going on here?
Oh, wait, do you have to do these minus?
Why don't our correlations match? What did we actually calculate with our z-scores? Let's think about this for a second. Yeah, go ahead. So they're both standardized, right? Both of the z-scores are standardized. Let's think about what we did with the z-scores, though.
We subtracted.
We subtracted the d-scores, the z-scores, so we got the difference, right? What are we really looking at? What is this 0.34 actually? It's actually, it is the distance between z1 and z2, but a better way to think about it, it is the discrepancy between z1 and z2. It's the amount, the standardized amount that they are not related. How do we get the standardized amount that they are related then? Yes.
You're saying
If we just say equals 1 minus this value, now we have the actual correlation, right? We calculated the discrepancy or the error in our z-scores, and in order to get the overlap, then we have to subtract it from 1. Right? When we talk about correlations, one of the things that this was in the video. I'm just going to pull this up here for a second. In regression analysis, one of the things that we do in regression analysis is we're trying to identify overlap, right? And so a correlation is really the extent to which one variable overlaps with the other variable. It's not the overlap of both variables, right? And in order to get the overlap of both variables, we have to do one step within that correlation. What do? We square it, right? And once we square that, we get the amount of variance that is explained due to this overlap, right? The amount of shared variance across each other, and then you can talk about it in terms of both variables. And here, the squared variance is .43, and that says that what? What do we conclude from that?
Is that going to be, that's your R squared, right?
Yeah, so what does R squared mean? That's all I'm
Yeah.
asking.
I guess the percentage of variance in Y that can be explained by X.
Yeah, or vice versa.
But I don't really understand what we mean when we say explained by.
So,
I just know that's what I'm supposed to say.
yeah, so it's not, I mean, so going back to our height example, right? If all men are 6 feet tall and all women are 5 feet tall, the best that we can do is 5'6". I'm sorry, would it be better if I say all women are 6 feet tall and all men are 5 feet tall? Am I
That would make it more
perpetuating?
comfortable.
I mean, I'm not perpetuating a stereotype. Men are statistically significantly taller than women, right? Like that's just the way that it goes. But if we have a predictor in there, such as gender or biological sex, and we use that to predict height, we can predict it perfectly, right? Which means that the overlap between those two variables is complete. When you set them on top of each other, there is no other variance that can't be accounted for, right? If you think of a variable having a mean right in the center of a circle and a bunch of dots that are spread out all over that mean, then when you set those two things on top of each other, they completely cover up. Every height is covered up by male or by female, right? That's unfortunately not ever the case with anything, right? Like basically nothing explains anything perfectly. And so what we're saying is that there are, when you set these kind of circles on top of each other, there are times when the dots match up perfectly or very close to perfectly, right? And then there's times when they don't match up at all. And so the variance explained is what we're able to say based on the deviations that we've got using this very common formula that says like here's how much these things vary standardized, right? If we take the mean of how much these two things vary, we can say that if they don't have any vary, right? If they don't vary at all, then that's a perfect explanation. And when they vary a little bit, then that explanation is subtracted from 1 to get to a percentage that they are perfectly explained. Does that make sense?
Sounds like we know that we're looking at the total variance, and we just kind of do like a percentage of that total variance that is.
Yeah, so that's a good point. We can calculate variance, right? We just calculate the standard deviation. You can figure out what the variance is very easily from the standard deviation, right? Which is what? What's the
Square.
Yeah, just square it, right? If you square something, so we can know what the variance is of a thing. And so if we say that like the variance of this is 8 units, right? Which is linear, by the way. It's additive. You can add variance. You can't add standard deviation. And so anyway, the variance is linear. So you can say like, okay, if the variance is like 25 units, then we can, which is different than the standard variance, right? Which says like the average amount of variance for any given person should be about this away from the mean. But if we know all of the variance, let's say it's 25 units, and we say that we can explain 50% of the variance, then that means that we can account for 12.5 units of variance in in something, right? And then we can add another thing that might account for another 5 units of variance, right? That doesn't overlap with the 12.5 that we've already got. And so the goal is to try and place enough circles over y that there's no more left. It never happens, right? You can't explain anything 100%. But statistics is great because it means you never really have to say that you're right. You just have to say there's a probability that I'm right. But yeah. Okay, so part of your homework is going to be calculating a correlation coefficient by hand using Excel. So you guys will be doing that. And the data set, I think, is a lot larger in the homework. So we will, you guys can have some fun doing that. Let's take a short break. When we come back, we're going to start focusing on regression.